So we looked at the voltages, you can also see what happens to the currents. So I have time axis, space axis, right? This is point A, this is point B, right? So we have the same situation. We have demarcations that are 1 microsecond apart. Okay. So we can draw the same echo diagram for the currents as well. And remember that the current at any point, right, for the forward voltage is V plus by Z naught, and for the backward voltage it is minus V minus by Z naught. Remember that current is directional, right? So when there are two currents going in opposing directions, the net current would have to be the difference of those two, right? So as long as you keep that in mind, I think there will be no issues. So remember that the steady state current that we solved from the last slide was about 40 milliamps, right? So we expect that amount of current to be flowing through the entire transmission line, right, at steady state. How did we get this? 12 volts divided by 300 ohms, right? So we expect ISS for t equals infinite, right? So okay, so we are going to approach 40 milliamps, but just like in the case of voltages, we will also approach this steady state current in steps, right? So let us try to understand what these currents will look like, right? So remember the V plus that we had going was 4 volts, right? So the current I plus would be 4 volts divided by the characteristic impedance Z naught, 50 ohms, right? So this would be 80 milliamps. Okay, so we are actually overshooting, right? So the current that is actually flowing in the transmission line, right, is actually higher than the steady state current, right? So we launched 4 volts into the transmission line, which corresponds to a current of 80 milliamps. Okay. Now in this direction, we said V minus was 2.4 volts. How did we get that? We had a gamma S, right? So let's recall Ts was 1/3, which was also equal to gamma S, and gamma L was 3/5. Right? So we said that 2.4 volts would be sent back, right, at the load. This would correspond to an I minus, which is minus 2.4 by 50, right? Or you can just say that current is going in the backward direction, right? Current is a directional quantity. So minus 2.4 by 50 is about 48 milliamps. Okay. So the current, if I were to start my plot for I at point B. So let's demarcate the points A and B again. Okay, I'm looking for when does current start flowing through the load, right? We actually see that there is no current flowing through the load for the first 1 microsecond, and then there is a jump to a value which is 80 minus 48, right? So about 32 milliamps. Okay, how did I get that? It's simply IB is equal to I plus I minus, and this was 80 minus 48, giving you 32 milliamps. Okay, so even though 80 milliamps of current was flowing through the transmission line, the reflection robs off 48 milliamps, if you want to think of it that way, allowing only about 32 milliamps starting to flow through the 200 ohm load starting from 1 microsecond, and this would last for another 2 microseconds, right? So I would expect this 32 milliamps to flow from 1 microsecond to 3 microseconds, right? Whereas if I were to look at point A, I notice that it already has started at 80 milliamps. Okay, and it's going to stay at 80. We are going to see that it's going to reduce after 2 micro, right? We'll see what it reduces to at 2 micro. So remember, after this reflection at the source gamma s, we now had 0.8 volts traveling in the forward direction, right? This corresponds to an I plus of 0.8 by 50. So this is about 16 milliamps, right? So if I want to know what is the update to the current at point A at 2 microseconds, I would simply have to add all the currents, right? So you had I at A at t equals 2 microseconds would be 80 minus 48 plus 16, right? So that would be 48 milliamps. So at 2 microamps, I am stepping down to 48 milliamps. Remember, the steady state is 40 milliamps, right? and I started off at 80 milliamps at the input point A, right. So, I would have to slowly step down from 80. The first jump is to 48 and then asymptotically I will reach 40. At point B, what is happening? The current is actually increasing from 0. It jumps to 32 first and then to some other quantity between 32 and 40, and eventually it will reach the steady state of 40 milliamps. Okay, so say that this is 40 milliamps. Similarly, this is 40 milliamps. You will have some sort of a asymptotic behavior. Okay. So, hopefully this example has given you some clarity on how exactly we use these voltage reflection coefficients both at the source and the load and the transmission coefficients to essentially estimate quantitatively what are the voltages and currents at the input and the load end for all times, right. Again, I would like to emphasize that this is only a transient behavior, right. According to circuit theory, at steady state, the transmission line can be replaced with a short, right. But if I am concerned with how the voltage actually reached steady state and that it took a certain time delay in order to reach the steady state value, I want to know how exactly it has taken the path to reach this steady state current or steady state voltage. You now have a very clear picture, right, both a mathematical background as well as an intuition, right, to following or tracking these voltages along the transmission line, right. So, you can, just like I mentioned for voltages, that these capacitors that we have to model the transmission line, right, that the entire transmission line is getting charged up to different voltage values. You can think of currents in terms of the magnetic fields, right, that are storing the energy within the transmission line. You are slowly charging up all the inductors, right, and then you are doing this in a very time delayed manner, right. So, while this is all great, okay, I have taught you the mathematics behind it. You've been given an algorithm, right, by drawing these echo diagrams to essentially estimate what is the voltage and current.